Welcome back. So last time we talked about partial fractions and we did two examples that showed how partial fractions will work. The big idea here was we had a rational function where maybe we've already done long division to make sure that the degree in the top is smaller than the degree in the bottom. We can then use this partial fractions process that we saw in the last video to uncommon denominator them, bust it up into separate fractions. Each of those will be much, much, much easier to integrate. So what we didn't talk about last time, of course, is how do you decide how to put those A's and B's and C's that we were using into your partial fraction decomposition? How did we decide to bust it up the way that we did? So we spent all that time just doing some examples and seeing the what. Now we need to learn some of the why. So here's the general rule. If you have a linear term in the denominator, so if your denominator is like x plus 2 when you bust it up, then you just get a constant. You just get like an a. So we saw lots of examples of that in the last video. Then we had an example where we had an irreducible quadratic that was in the last video was x squared plus 4. It got a bx plus c on top of it. So that's happens whenever we have an irreducible quadratic term. Okay? Now you might say, okay, what happens to third degree terms? Well, if you remember back in algebra, and again, there's no calculus in this at all. This is all just algebra. When you have a third degree polynomial, you can always factor it and break it down into linear terms and quadratic terms that don't factor with real numbers. They would with complex numbers, but as I said before, I'll refrain from talking too much about those. You get only linear terms or quadratic terms. A cubic or higher could factor some more and break down into just linear pieces and quadratic pieces. Or maybe you might have them repeated, like you might have an x plus 2 squared, okay, or the whole thing squared. Those kinds of multiple terms get repeated in our decomposition. So here's an example. This is nasty, right? I would never ask you to take something that was that ugly and complicated and find all the A's, B's, and C's on an exam. But what I very well and very likely could ask you to do on an exam is to, quote, set up the partial fraction decomposition. In other words, write down what I'm about to show on the screen. So tell me what goes over what when you start the partial fraction process. That way I can ask you to set it up like this, and so that I know that you know how to do it, and I only have to ask you maybe one that you work completely out all the way, and I still know whether you know how to do all the other varieties also. So what's our first term? First term in the denominator here is the x minus 2. It's just an x minus 2 linear term, right? X minus 2, no squared there. So it just gets an a, just a over x minus 2. Super easy. Next up, x squared plus x plus 7. Well, it looks like it's quadratic. Does it factor? Well, if you play with it, you can see that no, it doesn't factor. Or if it did, it would have to use complex numbers. You could use the quadratic formula if you wanted to convince yourself to see that the roots are complex numbers. So this is an irreducible quadratic, so it gets a bx plus c on top of it. Okay, we come to the next one. Whoa, wait a minute. X plus 4 cubed. I thought you said you could always factor cubics some more. Well, you can. They'll factor into linear pieces like this one, but there's three of them. There's x plus 4, x plus 4, and x plus 4. There's three of them. Those are repeated linear terms. It's just an x plus 4, but it's been copied three times. There's three of them down there. So what you have to do is each one will get a single letter on top of it, but we have to repeat it three times. So what will happen is we'll get a d over x plus 4. Again, just one single letter because it's a linear term. Just a d over the x plus 4. But there were three x plus 4s, so I have to repeat it three more times, or two more times. I have to repeat it to get three times. I have an e over x plus 4 squared and an f over x plus 4 cubed. And you think, wow, that looks weird. There wasn't an x plus 4 squared to begin with. I know. This is the way that it works, though. If you have a linear term, and there's lots of them, say there's three of them, you have to repeat it three times. a d over x plus 4, an e over x plus 4 squared, and an f over x plus 4 cubed. So notice it's not the same x plus 4 every time. It's an x plus 4, an x plus 4 squared, and an x plus 4 cubed. Okay? Um, so at this point you go, why? Why do you have to do it? That looks weird. Well, the answer is if you don't do it this way, then you get a system of equations that you can't solve. So this is what works. When you break things up and uncommon denominator them, this is the way you have to do it in order to be sure you get something that you can actually solve when you try to figure out what the A's, B's, C's, and D's and so forth are. Okay, last bit. This is a irreducible quadratic, x squared plus 1, and it's in there twice. It's x squared plus 1, the whole thing squared. So an irreducible quadratic gets a gx plus h on top of it, but it's repeated. Notice there's two of them down there in the denominator. So not only do I have an x squared plus 1, I also have an x squared plus 1 all squared. And it gets an ix plus j on top of it. Wow, okay. So it'd be nasty to try to figure out what A, B, C, and all those other things up to J are without using a calculator, of course. If you plug this into Wolfram Alpha or something, it'll spit it right out. But on the exam, you won't have to find something that's that many letters. You also won't have to find things where the numbers are so terrible, but you won't have a calculator either or access to the internet. So the good news is all we're really doing here is just algebra. There's no calculus in any of this at all. So here's an example. I've got a cubic in the bottom, x cubed minus x squared minus x plus 1. So step one is to try to factor it. Well, okay, so on the homework, you might have to factor it, play with it and see. On the exam, I wouldn't make you factor something like that unless you could just factor an x out immediately because it's too much work to try to factor a cubic by hand. So here's what it actually comes out to be. So on an exam, I would give you something pre-factored or easy to factor. So here I have an x plus 1 and an x minus 1 squared. So this is so we get a chance to deal with a repeated term, right? So when we bust this guy up, I'll have an a over the x plus 1, but then the x minus 1 gets a b, and then the x minus 1 squared, right, because I have to repeat it, gets a c. Now I need to write down my main equation, and I'm off to the races to figure out what a, b, and c are. Well, almost. There's one little wrinkle that we want to be careful of. So you remember in the last video I said that when we get this next equation here, we're not just cross multiplying, okay? Even though it kind of looked like it. In both of those examples in the last video, it looked like what we had done was just cross multiply, but it's not. What we've really done, right, to figure out this next equation is taken the A's, B's, and C's part that we busted up into three separate terms and asked ourselves if we recommon denominator them, right, what would we get? Well, we should get this original thing we started with, and the numerator in particular should be 4x. So if we're careful, we can figure out what the numerator over here would be and set that equal to 4x. And that's what I've done in this equation. But let's look carefully at what this is. So this is a, right? Well, let's do it the right way instead of talking about what would be wrong. The right way to do this would be to ask yourself, what's my common denominator? Well, oh, there it is. It's x plus 1 times x minus 1 squared. So I've already got an x plus 1. What would I need to multiply, the top and bottom, to get back here? I'd need to multiply by x minus 1 squared in the top and bottom so that the denominator would be x plus 1 and x minus 1 squared. So multiply the top and the bottom by x minus 1 squared. So the a x minus 1 squared would be the first part. Next term, I have a b. It already has an x minus 1. So what would it need to be multiplied by, top and bottom? Well, it's already got an x minus 1, so it would need an x plus 1, of course, and just one more x minus 1. Right? So here I get x plus 1 and x minus 1. I don't need an x minus 1 squared because I already have an x minus 1. Right? It just needs one more to get x minus 1 squared. What happens to my c? Well, it's already got an x minus 1 squared. Right? So all it needs is the x plus 1. So the c just gets the x plus 1. If I do that right, then that's what the numerator would be if I recommon denominator at the right-hand side. That would all be equal to the original numerator, the 4x, and I'm good to go. Now, what causes people problems sometimes is they do those first few examples that we did in the last videos, and they think, oh, we just cross multiply, right? And then they try that here, and there's no way to get the right answer if you were to quote cross multiply here. In other words, I don't do a times both of these terms, x minus 1 and x minus 1 squared, because I don't need both of them to recommon denominator it. I just need the x minus 1 squared. Similarly, the b doesn't get both of these terms, x plus 1 and x minus 1 squared, because it's already got an x minus 1. And the c doesn't get both of these. It just gets what it needs to make the common denominator work. And if you don't do it right, instead of equal to 4x, you just get an unholy mess and you never get the right answers for the a's and b's. So it's not very hard. It's just a matter of remembering what we're really doing, which is we're taking a fraction and busting it up into three different pieces. This is why this is called partial fractions. We're taking a fraction and we're busting it up into parts. Okay, well, I'm going to do the Heaviside method with this one again because this this won't be too bad. There's easy ways to knock out some of these terms. For example, if I let x equal 1, well, that gets rid of the a's and the b's, right? When I plug 1 in, this will be 0. When I plug 1 in, this will be 0. So all that's left is 1 plus 1 is 2, c, equals 4. So ding, 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 c is equal to 2. We're done. Similarly, I can try sticking in negative 1. When I stick in the negative 1, the b and the c goes away, right? Because this part will be 0, this part will be 0. This leaves me with negative 1 minus 1 is negative 2. Squared becomes plus 2, which when our squared becomes plus 4. So I have 4a equals 4 times negative 1 gives me negative 4. So divide the 4 over, and a has to be minus 1. That was easy, right? So this is really cool. It's just algebra, right? Okay, so how do I figure out what the b is? Well, there's nothing that will get rid of a and c at the same time. So we just pick another easy number, and the easiest number is probably 0. Plug that in and see what we get. When we do, we still have a's, b's, and c's left, right? The right-hand side, 4x becomes 4 times 0, so that's easy enough. But remember, we already know what a and c are, so I can plug those in. So a was negative 1 from a few minutes ago. C was 2. So negative 1 minus b plus 2. Altogether, that gives me that b has to be 1. So that's really cool, right? The Heaviside method works here. You could also collect all the like terms. This one would be a little harder to do that because we'd have to FOIL out the x minus 1 squared right there, and the algebra would get really ugly. The Heaviside method works really fast. All right, so when we go back to our original problem, knowing that the a, b, and c were negative 1, 1, and 2, there's what we get, all busted up for our integrating pleasure. So first term is really easy. That's a negative 1 over x plus 1. Of course, when we integrate that, we'll get a log. Second term, we'll integrate that and get a log. The third term isn't going to be a log, right? And so maybe it's worth taking a second to point out why. Right? So the first term, remember, I'm really doing u substitution, but really quick, letting u be x plus 1. Right? So I'll have negative log of absolute value of u, or x plus 1. Same sort of thing here. Not negative anymore because it's a plus 1. Plus log of absolute value of x minus 1. So why don't I get log of x minus 1 squared? Right? Well, remember, that's not the way that integration works. This is stuff squared in the denominator, not just stuff. So what I really have is like a u squared in the denominator. Or a better way to think of it is u to the negative 2 power. So how do you handle u to the negative 2 power? That becomes u to the negative 1 power divided by negative 1. So again, this is u substitution, but done really quickly because we're all so used to it now. We get x minus 1 raised to the negative 1 power over -1. And of course, the 2 that was our original c is still hanging out there in front. And don't forget, don't ever forget the plus c at the end. So, makes sense to everybody? Part of what excites me about this is that, again, we're just doing algebra. It's new algebra maybe and somewhat unpleasant algebra, but it's still just algebra. In fact, if it helps you feel a little better, the truth is this whole partial fraction process is usually in every college algebra textbook. And this used to be a really common topic to cover in high school algebra. This would be something everybody would see in the 10th grade. Over the years, people have taken this out of 10th grade algebra, and even though it's in almost every college algebra book, most people don't cover it when they do college algebra because, well, you don't really need it for much of anything in college algebra or in high school. Where you really need it is right now. So here's where we're going to get it. Um, Here's another example, right? So x minus 1, that's linear, over x squared plus 2x plus 3, that's quadratic. So the degree in the bottom is bigger than the degree in the top. It doesn't need to be long divided or anything. It just is ready for the partial fraction process, right? Well, sort of. So this is actually a harder integral for most students than you would think. And the reason is it's already been partial fractioned. What's happening in the denominator is it's irreducible, right? So that x squared plus 2x plus 3 doesn't factor. This is what you would get if you had done partial fractions to something harder, right? What we've really got in the numerator, that x minus 1, that's like an ax plus b up there. So this is the kind of integral that you'll get maybe at the end of a really, really long partial fraction problem, where this was an irreducible quadratic, and what's happening in the top is 1x minus 1 is our ax plus b. So this kind of integral is a good thing because we don't actually have to partial fraction it. It's already been partial fractioned, right? It's just ready to be integrated. The problem is this is actually a little harder maybe than you might think, especially when you first look at it, because people will look at this and they'll do all kinds of crazy stuff. Um, Sometimes people will try to always just make it a log because they see stuff in the denominator or other weird stuff. The trick is, well, let's complete the square. Let's make it look like we have stuff squared plus stuff. If you remember, this was the same trick we had to do when we were dealing with um, trig substitution, and we had a quadratic like this inside of a square root. The first step was to complete the square so that it looks like stuff squared plus a squared, or maybe u squared plus a squared. So if you remember the whole completing the square business, well, we'd take this 2, we would cut it in half. It gives us 1. So we have to stick the 1 in here. We have added 1 squared in order to make our square part. We usually have to subtract 1 on the outside, so this 3 becomes a 2. And by adding 1 to the 2x, this whole thing, well, factors now into x plus 1 squared, and we still have our extra plus 2 on the outside. So that's just the completing the square stuff. We've done that before. Now we do u substitution. Let the u equal 2x plus 1. Du is dx. That's really cool. So we end up with u squared plus 2, and the du, of course, is the same as the dx. And you think, oh, this is awesome, except wait a minute, why are we doing u substitution? This doesn't work, right? If I try doing u substitution, I've got this extra x. Well, that's right. And almost always, this would be a sign where we go, up, put our hands up, we're done, not a problem. This is not a problem we can deal with. Something is horribly broken. I tried to do u substitution and it didn't work. There was an x left over and I can't do it. And you're right. Almost always, that's the sign that u substitution isn't going to work. When I got an extra x left over that I can't do anything with. Well, sort of. Let's go back and look at what we did here. U was x plus 1, right? Let's stare at that for a second. What does that make x? right? This is sort of like when kids are on the playground, and they start calling each other names, and um, you know, I know you're one, but what am I, right? Okay, so what is u, right? U is x plus one. So what does that make x? Well, x has to be u minus one. Oh, okay. Well, then in this special case, when we can solve for x, then we could make this work. I could take x equal to u minus 1 and stick it right there where the x was before. So this becomes u minus 1 minus the 1 that we had before, all in the numerator. So altogether that gives us, well, u minus 2. And I do what I did before. To my u minus 2, I bust that joker up into two separate integrals, a u over u squared plus 2 and a negative 2 over u squared plus 2. Okay? That's the right way to separate these out. We've uncommon denominated them all the way as far as they'll go, and now each of these two pieces will be easy to integrate. Okay? So again, moral of the story, if you end up with an irreducible quadratic in the bottom, like it's already been partial fractioned, right, and a nice linear term above it, the trick is complete the square, do u substitution, then bust that thing up into two separate integrals with the u, right? So u over the u squared plus 2 and negative 2 over the u squared plus 2. The reason is these two integrals integrate differently. With a u right here, right, we can do, well, I was about to say u substitution. We've already used u. It'd be sort of like a double u substitution. It's a horrible pun. And if I were going to write out all the details, I might call the denominator here double u, right? Because the derivative of the denominator would be 2u. And sure enough, I have a u in the top to make that work. So I have to put a 2 here, put a half out front, and that would give me 1/2 log of my double u, this denominator, absolute value of u squared plus 2 there. On the other hand, the second integral, right, if I take that negative 2 and factor it out, put it outside the integral, I have 1 over u squared plus 2. And this, again, is screaming out, I'm an inverse tangent. I'm a little inverse tangent, short and stout, right? U squared plus 2 squared. I need to think of this number as an a squared. So I have to think of that 2 as being square root of 2 squared. My a is square root of 2. So I'll end up with the negative 2 on the outside. Then when I integrate this, I'll have a 1 over square root of 2 on the outside because its integral will be 1 over a, inverse tangent of u over a, and the a is the square root of 2. Then the plus c. Now I have used u's, so I have to go all the way back to x's by substituting back in the x plus 1's where I now have u's. But so actually, there was nothing here that was even algebra. I've been saying all along that we're not really doing any calculus here. We've just been doing algebra. In this last example, there really wasn't even any algebra. The trick was just to realize that this was an integral we really already knew how to do. We just had to complete the square and separate the pieces so that we could recognize how to integrate it.